The new spectral data on 3I Atlas are nothing short of extraordinary. From the very first moment these results began to circulate among the analysis teams, it became clear that this interstellar object is not merely different from everything we had been observed before, but that it decisively shatters several scientific expectations that had been held about travelers arriving from outside our system. As the most sensitive instruments began to record its spectral signature, the behavior of carbon dioxide, the response of the dust to solar radiation, and the optical texture of the coma started to reveal patterns that do not fit any comet of solar origin ever studied. Until now, specialists in infrared spectroscopy had noted that the ratio between carbon dioxide and water reached a surprisingly high value, something almost impossible to find in comets formed in our cosmic neighborhood. Meanwhile, polarimetry teams were observing strange optical behavior that suggested the surface of the material enveloping the nucleus had been shaped by extremely harsh conditions, probably during an immensely long journey through interstellar space. With each passing day, new analyses add pieces to a puzzle that appears to have no comparison. The thermal models do not fully explain the amount of activity it displays. The dust dynamics do not behave as expected. For an object of its size and composition, the intensity of certain spectral lines points to irradiation processes so prolonged that it is difficult to imagine how much time it has spent drifting far from any star. All of this leads researchers to describe these data as something that exceeds the boundaries of accumulated experience with local objects. And yet, what is most intriguing is that each new observation does not reduce the mystery but widens it. Before continuing with the in-depth analysis of 3I Atlas, it is important to make clear why this object has become the center of so much scientific attention. It is not just another comet. Nor is it a casual visitor that passed discreetly through the solar system. It is a confirmed interstellar body, a traveler formed in an environment completely alien to ours, with a distinct chemical history, a different type of ice, and an energetic record that reflects millions or perhaps billions of years exposed to deep space. And now that new spectral data have been obtained from various observatories, both in space and on the ground, it has become evident that 3I Atlas does not follow the usual patterns that astronomers use to interpret the activity, composition, or thermal behavior of a comet. That is what has sparked such interest, the opportunity to study an object that did not originate here and that is revealing properties never recorded before. What you are about to read is a continuous and entirely scientific narrative, guided by the most recent studies on the composition, the activity, the interaction with solar radiation, the effects of galactic cosmic ray bombardment, and the optical evolution of the material surrounding the nucleus. Nothing fictional, nothing exaggerated, only pure science about an object that is displaying behaviors that force us to rethink what we thought we understood about interstellar travelers. From the moment 3I Atlas was detected, the observation teams understood that they were not facing an ordinary object. The hyperbolic trajectory, the unusual speed, and the direction of approach already suggested it was coming from outside the solar system. But what really began to change the way researchers approached it were the first spectral records. Within days, ground-based and space observatories started reporting signals that did not match the chemical profiles typical of a comet originating in the outer regions of the solar system. Normally, when a comet becomes active for the first time, water is the dominant molecule in its spectral emission, and around it revolve the lines of carbon monoxide, methane, ammonia, and other volatile compounds. However, in 3I Atlas, the carbon dioxide signature stood out in such a marked way that the teams had to repeat observations just to make sure there was no kind of instrumental interference. When the space telescope that performs infrared observations confirmed that the ratio between carbon dioxide and water reached extremely high values, experts began to review theoretical models about the formation of ices in other stellar systems. Carbon dioxide is not rare in comets, but the amount present in 3I Atlas exceeded by almost an order of magnitude what has been measured in local bodies. This led to the thought that the object must have been ejected from a system where the temperature, radiation, and density conditions of the protoplanetary disk were very different from those that characterized the birth of the solar system. The partial pressure of carbon dioxide required to form dominant ices rather than mere minor components indicates that this interstellar visitor may have originated in an extremely cold region of a young disk, or perhaps in a carbon-enriched chemical environment. At that stage of the study, many astronomers were already speculating privately about the effect of galactic cosmic rays. These are highly energetic particles that cross the galaxy and, over time, can modify the chemical composition of surface ices. The most recent evidence suggested that 3I Atlas had been bombarded for so long that part of the carbon monoxide originally present in its structure could have been chemically transformed into carbon dioxide. This would explain why the carbon dioxide signal was so strong even at great distances from the Sun, when water ice activity is usually minimal. The idea that the object preserves a surface layer transformed by millions of years of exposure to the interstellar medium began to fit the optical data, since the coma displayed a coloration and light response that also did not match those observed in solar system comets. As it approached the Sun, a natural increase in activity was expected, but the patterns of dust and gas ejection did not behave as those of a typical comet do. The jets appeared to react to temperature variations in a nonlinear way, as if there were zones of the nucleus that responded more quickly than normal to small changes in solar radiation. This led the teams to consider the possibility that the interior of the nucleus was formed by layers of materials with different thermal histories, something possible in such an ancient object. The early activity dominated by carbon dioxide reinforced the idea that the outer layers had been modified, while the interior might contain a more representative mixture of its original composition, although that could only be confirmed with observations after perihelion. The polarimetry records added an even more unusual dimension to the case. The way sunlight scattered in the comet's dust was generating a more pronounced and prolonged negative polarization than that of any known comet. In practice, this means that the dust particles do not have a conventional structure of fine, porous grains like those observed in solar system comets. On the contrary, they appear more compact, more processed, and possibly coated with complex organic materials formed by the prolonged action of cosmic radiation. This matches laboratory-studied models of cometary material aging, where it has been shown that long periods of irradiation can darken, compact, and harden the surface layers. The combination of all these phenomena began to paint a unique portrait of 3I Atlas. It is not simply an interstellar comet. It is a physical archive of chemical and energetic conditions outside our system. Each spectral line, each variation in brightness, and each change in the coma represents a piece of information about places we can never visit directly. That is why, from the beginning, the analysis of these data was not considered just another study, but an opportunity to understand how solid bodies form and evolve in other corners of the galaxy. And as the observatories continued to record its approach, it became clear that this object was going to keep surprising even the most experienced teams, because nothing about it seemed to fit the usual patterns that have guided the understanding of cometary activity for decades. The amount of carbon dioxide, the optical response of the dust, the thermal signature, and the first signs of anomalous activity indicated that what we were seeing was only the beginning. As 3I Atlas moved deeper into the region where solar radiation exerts greater influence, the specialists knew that decisive moments were approaching for interpreting whether this highly unusual behavior would persist, intensify, or reveal new elements not yet recorded would appear. When 3I Atlas began to draw closer to the inner solar system, the teams prepared for a significant change in the quality of the spectral data. As a comet receives more solar radiation, the energy absorbed by its ices enters a much more dynamic sublimation state, and that allows instruments to detect with greater clarity which molecules dominate the activity and how they are being released from the surface layers. With 3I Atlas, that transition not only permitted sharper data, it revealed unexpected behaviors that further widened the gap between this object and comets formed near the Sun. The first measurements close to perihelion confirmed that the intensity of carbon dioxide remained disproportionately high, even when water ice should already have begun to show clear signs of dominant activity. The specialists compared these data with those of local comets observed at equivalent solar distances and discovered that none displayed such an exceptional profile. It was as if 3I Atlas were composed, on its surface, of layers where carbon dioxide was not only abundant but had been preserved in a profoundly different way. Another aspect that drew attention during this phase was the appearance of thermal patterns that did not match standard cometary response models. Normally, as a comet approaches the Sun, its surface experiences zones of gradual heating, where radiation penetrates the outer layers and activates volatile materials according to depth and nucleus composition. But in the case of 3I Atlas, the thermal map revealed rapid, localized fluctuations, as if certain regions responded abruptly to the increase in radiation. These variations could indicate pronounced structural differences within the nucleus, possibly caused by the object's unique history. If it has spent millions of years exposed to interstellar space, it is likely that some layers have been chemically transformed by cosmic rays while others have remained relatively protected. This kind of internal contrast is not common in local comets, whose evolution is more regulated by interactions with the Sun and thermal processes within the solar system. While the thermal models were being recalibrated to try to reproduce that irregular temperature distribution, the optical data continued to provide key information. The reddish coloration detected in the coma was not merely aesthetic. It represented a chemical fingerprint of long-duration energetic processes. Dust grains subjected to high-energy radiation tend to darken and acquire more intense tones due to the formation of complex organic compounds. In specialized laboratories, researchers simulate charged particle bombardment on carbon-rich particles, producing dark residues similar to those suspected to coat the dust grains of 3I Atlas. This matches the polarization observations that indicated the dust structure did not resemble that of fine, porous, young particles, but rather aged and compacted materials. The team studying dust dynamics also noted differences in the way particles detached from the nucleus. In typical solar system comets, coma expansion usually follows relatively predictable patterns based on gas velocity and the mass of ejected particles. But in 3I Atlas, some particles appeared to move at velocities that did not match the standard gas-to-dust relationship observed in other comets. This is believed to be related to the composition of the dust itself, since more compact grains tend to react differently to the pressure of sublimated gas. Moreover, the size of these particles may have been influenced by prior processes that occurred long before the object entered the solar system. If the dust has been processed for millions of years, it is possible that it has undergone cycles of compaction, microscopic fractures, and organic coatings that alter its mass and surface. Another relevant aspect that emerged at this stage was the analysis of spectral lines related to short-lived radicals and molecules such as cyanide and dicarbon. In local comets, these molecules usually appear in well-studied quantities that allow comparisons between objects. However, in 3I Atlas, some of these compounds appeared to show intensities that fluctuated more than expected. Although not impossible amounts, they did imply non-standard behavior. This led researchers to consider the possibility that the nucleus surface was a heterogeneous mixture with different levels of accumulated exposure, which affects the release of radicals when certain ices sublimate faster than others. This type of heterogeneous configuration has been observed in some solar system comets, but not with such an extreme combination of carbon dioxide activity and organic radical signals. In parallel, orbital dynamic studies confirmed that its trajectory remained consistent with a genuine interstellar object, which ruled out any possibility that it had previously been captured by the Sun or by planets in the solar system. This is essential for interpreting its properties, as it allows us to assume that its composition reflects a completely different chemical environment from ours. The specialists argue that studying this object is equivalent to observing a physical fragment of another stellar system, a piece of cosmic history detached from a place we can only imagine through theoretical models. Each molecule present in 3I Atlas is a clue about the conditions of that environment, from the temperature of the protoplanetary disk to the intensity of local radiation. While the coma continued to expand, some instruments recorded weak signals of possible more complex organic compounds, although they had not yet been definitively confirmed. These hints have led some teams to plan deeper analyses, because the confirmed detection of advanced organic compounds in an interstellar object would be a huge step for astrobiology. It is not about suggesting life or biological processes, but about understanding how organic molecules can form and be preserved in environments outside the solar system. If 3I Atlas preserves organic material processed for millions of years, it could represent a real example of the chemical building blocks that circulate throughout the galaxy. At this point, the main conclusion of the teams is that this object is revealing a complexity that exceeds what was anticipated. Its activity, its chemistry, and its response to solar radiation position it as a key piece for understanding the diversity of interstellar bodies we may encounter in the future. The radical differences between its behavior and that of local comets do not imply anomaly or danger. They imply diversity and scientific richness. And as it continues its journey around the Sun, many observations remain to be analyzed that could reveal even more unexpected aspects. When 3I Atlas continued moving after perihelion, the instruments dedicated to spectral follow-up began to record a behavior that surprised even the best-prepared teams. The scientists expected that after the point of closest approach to the Sun, the interstellar comet's activity would show a predictable transition, a gradual decrease in the intensity of volatile gases and a progressive change in the observed composition as the outermost layers of the nucleus lost material. However, that is not what happened. Instead of showing a uniform drop in activity, 3I Atlas displayed irregular variation in the emission of different molecules, as if some regions of the nucleus were responding asynchronously to the loss of solar heat. This pattern, far from being an instrumental error, was confirmed by several observation stations around the world, leading to the conclusion that the nucleus possesses a more complex internal structure than initially thought. One of the first indications of that internal complexity was the way carbon dioxide continued to stand out even in the post-perihelion phase. With solar system comets, carbon dioxide tends to decrease rapidly once they move away from the Sun, since the active layers are usually depleted and water ice regains a dominant position in the residual activity. But in 3I Atlas, the intensity of carbon dioxide maintained an unusually high rhythm, as if there were deep deposits that continued to be released in a sustained manner. This implied that the distribution of volatiles within the nucleus is not homogeneous. Moreover, it suggested that part of the carbon dioxide was not located in surface layers but in protected regions that only became activated when the perihelion heat managed to penetrate deeper than expected. This delayed reactive behavior led the specialists to confront models that describe how heat propagates inside an interstellar cometary nucleus, and the preliminary results indicated that the thermal conductivity of the material in 3I Atlas might be different from that of local comets. Also during this post-perihelion phase, significant changes were observed in the distribution and size of the emitted dust. Instead of showing a linear reduction in coma density, some regions displayed sudden increases in activity. This could be related to internal fractures induced by thermal stress. When an object like 3I Atlas experiences such rapid heating and cooling, the outer layers can expand and contract unevenly, generating stresses that produce sudden detachments. This mechanism could explain why brief episodes of increased dust production were detected even when the object was already moving away from the Sun. For the researchers, these episodes offered an extraordinary opportunity, since each exposed fragment represented possibly less processed material, which would allow clearer signals from the interior. Optical polarization observations also showed an interesting transformation after perihelion. The depth of the negative polarization point decreased slightly, which could indicate a subtle change in the composition or size of the particles that dominated the scattering of sunlight. This was expected, since the dust emitted during the outbound phase might come from layers less exposed to galactic cosmic rays, with properties more similar to those of freshly released grains. However, even with these changes, the polarimetric behavior remained distinct from that of solar system comets, reinforcing the idea that interstellar dust possesses unique characteristics that reflect its chemical and energetic history outside the solar system. The way light polarized in 3I Atlas continued to show patterns that could not be explained solely by the geometry of the coma or by variations in dust production, but by a differentiated composition and microphysical structure. At the same time, the emission spectra of organic compounds continued to show irregularities. At times, the presence of radicals such as cyanide showed a slight increase, which puzzled several analysts, because normally these compounds decrease steadily after perihelion, although no definitive conclusions have yet been reached. One preliminary interpretation suggests that these radicals could be associated with more complex organic materials that fragment when exposed to the internal heat released by the nucleus reorganization. This hypothesis gains strength precisely because of the interstellar nature of the object, since its prolonged journey through dense galactic radiation regions may have favored the formation of unusual molecular structures not common in local comets. Each detection of these molecules adds another layer of evidence to the idea that 3I Atlas is not only chemically different, but could contain a much broader molecular diversity than observed in most sunbound comets. During this stage, astronomers also focused on the evolution of the ion tail. Normally, as a comet moves away from the Sun, the ionic tail loses intensity rapidly due to the decrease in ultraviolet radiation that ionizes the gases. Nevertheless, in 3I Atlas, the ion tail showed variations that indicated more persistent ionization than would be seen in common comets. This could be due to the continued presence of highly volatile molecules released from deep zones of the nucleus that continue to be carried away by the solar wind longer than expected. This behavior also aligns with initial analyses suggesting that part of the internal structure preserves reserves of materials that activate with delays, thereby prolonging the spectral life of certain emission lines. On the physical level, the comet's departure also allowed study of how the nucleus loses energy, which is fundamental for estimating its internal structure. The thermal models adjusted to the data suggest that the nucleus might have a lower density than expected, indicating a highly porous structure with isolated internal chambers. This type of configuration can develop in objects that have traveled for extremely long times in low-pressure, low-temperature environments. If these internal chambers contain unexposed materials, then 3I Atlas could be revealing deep layers that never interacted with stellar heat until its passage through our system. In conclusion, the post-perihelion phase of 3I Atlas did not represent a simple decline in activity. It was a period of revealing transformations that offered a deeper look into the internal layers of the nucleus and into how an interstellar object reacts to heat for the first time after millions of years. The data obtained in this stage not only complement what was learned before perihelion, but also open new questions about the diversity and evolution of interstellar bodies. As 3I Atlas continued advancing through the outer part of the solar system after its closest passage to the Sun, the scientists took advantage of this stage to analyze in greater detail how the residual activity of the object revealed internal aspects that could not be observed before. Although most comets tend to stabilize their gas production as they move away, 3I Atlas behaved in a way that did not match that trend. The instruments continued to record carbon dioxide emissions in unexpectedly stable quantities, leading researchers to think that the heating caused by perihelion had reached deep zones of the nucleus, activating materials that had never sublimated in millions of years. This delayed release allowed the study of internal layers that in other comets are rarely exposed without fragmentation. Something that quickly captured the attention of the teams was the way the intensity of carbon dioxide appeared to correlate with changes on the nucleus surface. The adjusted thermal models suggest that when an interstellar comet like this experiences abrupt temperature changes, heat penetrates the nucleus unevenly, generating zones of tension that could cause internal cracks. These cracks, though small, can serve as channels through which gases trapped since very ancient times escape. In local comets this phenomenon occurs, but the trapped volatiles tend to be water or carbon monoxide. In 3I Atlas, however, the presence of carbon dioxide in deep regions implies very different formation conditions, possibly colder or with greater availability of gaseous carbon during its origin. The spectral observations of the coma also showed uncommon behaviors. As the object moved away from the Sun, some emission lines related to volatile organic compounds remained active longer than expected. This surprised the specialists because normally at this phase the more complex organic compounds fragment quickly. The persistence of these signals suggests that these compounds were being freshly released from layers that had never been exposed to intense heat. The idea that the nucleus contains isolated chemical pockets from the object's origin has gained strength and reinforces the notion that 3I Atlas is an extraordinarily valuable chemical reservoir for understanding formation environments outside the solar system. The evolution of the dust also offered revealing data. Sensitive instruments recorded that, despite the general decrease in activity, the emission rate of large particles did not decline at the same pace as fine particles. In typical comets, large particles usually lag behind and disperse slowly, while the production of small particles decays faster. However, in 3I Atlas, large particles continue to appear at rates indicating abrupt detachments from the nucleus surface. This could be due to the type of materials that compose the interstellar dust of this object, more compact, more processed by radiation and more resistant to surface fractures, but prone to detach in larger blocks when internal stresses exceed certain limits. Moreover, dust reflectance analyses revealed a gradual shift toward less red tones as the comet moved away from the Sun. This supports the hypothesis that the dust released after perihelion comes from less irradiated, more internal layers, less processed by galactic cosmic rays. Although it was still interstellar dust, its optical signature was slightly different from that of the pre-perihelion phase, implying that the chemical structure of the grains is not homogeneous throughout the nucleus. This internal diversity turns 3I Atlas into a unique source of information about how solid material evolves in an object ejected from its original system and subjected to extreme radiation cycles over millions of years. Another area that showed interesting behavior was the dynamics of the ion tail. As the solar distance increased, the tail should have become more tenuous, but the teams detected fluctuations in the length and intensity of the ionist emissions. The preliminary explanation is that the sustained activity of carbon dioxide maintained a constant flow of molecules that, when ionized by the solar wind, prolonged the life of the ionic tail beyond what is observed in local comets. This led some researchers to propose that interstellar objects might display more persistent tail structures due to their compositions dominated by volatiles that react differently to ionization processes. At the chemical level, one of the most interesting discoveries of this phase was the detection of slight variations in the ratio between certain organic radicals, although no definitive conclusions exist yet. Some teams suggest this could indicate the presence of more complex precursor molecules buried in intermediate layers of the nucleus. With solar system comets, organic molecules can undergo degradation processes during multiple solar passages, something that does not happen with an interstellar object like 3I Atlas, which is probably experiencing its first significant heating since formation. This opens the possibility that some chemical structures in its interior remained practically intact for millions of years, offering a unique window into chemical conditions of regions where direct observation has never been possible. The studies of density and internal structure also continue to be refined. The simulations suggest that the nucleus could be even more porous than initially thought, with an internal matrix full of interconnected cavities. This type of structure is not unusual in comets, but the depth and distribution of these cavities appear to differ from those observed in local objects. In particular, the ability of the nucleus to retain heat for prolonged periods after perihelion would imply an internal network of low thermal conductivity, something that matches materials that have been slowly compacted over millions of years without experiencing significant thermal cycles before reaching the solar system. Finally, the overall behavior of the comet at this stage reaffirmed that its interstellar origin is not just an orbital fact. It defines every aspect of its chemistry, its activity, its dust, and its evolution. The unusual persistence of carbon dioxide, the optical signatures dominated by dust aged by galactic radiation, the appearance of organic compounds in late phases, and the asymmetric response to solar heating form a coherent set that can only be explained by considering its history outside the solar system. When the research teams continued analyzing the data acquired after perihelion, it became evident that 3I Atlas not only challenged previous expectations but also forced scientists to compare its behavior directly with other interstellar objects. Although only 3 bodies of this type have been confirmed so far, each has shown radically distinct characteristics. One surprised by its lack of traditional cometary activity and its shape. 2 showed activity similar to that of a solar system comet but with elevated carbon monoxide levels and peculiar optical behavior. However, 3I Atlas seemed to place itself in an intermediate point while remaining completely differentiated. Its extreme carbon dioxide dominance had no precedent. Its dust displayed a unique microphysical structure, and its activity varied in a way no standard model had anticipated. This comparison among the 3 objects reinforces the idea that interstellar visitors represent a much greater diversity than imagined only a decade ago. One point the scientists highlighted during this phase was the way 3I Atlas responded to the decrease in solar radiation. Normally, a comet's surface cools rapidly when moving away from the sun, reducing the sublimation of the most common volatiles. However, the thermal measurements indicated that some zones of the 3I Atlas nucleus maintained elevated temperatures longer than expected. This led the specialists to speculate that certain internal cavities might be acting as thermal reservoirs where heat is trapped and released gradually. This prolonged heat retention could explain why carbon dioxide activity remained detectable even at distances where, in typical comets, it would have almost completely disappeared. In addition to this, the gas emission patterns showed a striking feature: small oscillations in intensity that occurred at irregular intervals. This behavior could indicate a rotating nucleus with variations in activity depending on which regions were exposed to radiation or cooling. Although nucleus rotation is not an unusual phenomenon in comets, the way it seemed to influence material release suggested an extremely heterogeneous structure. The experts began modeling scenarios where the nucleus could be composed of sectors with completely different thermal histories, the product of millions of years of uneven exposure to the interstellar environment. This type of internal distribution can occur when an object spends long periods without significant gravitational interaction, preventing internal processes from becoming homogenized. The dust continued to be one of the most important keys to understanding the object's history. Photometry measurements revealed that the coma showed subtle changes in density that seemed to synchronize with periods of large particle emission. These particles had optical properties distinct from those observed before perihelion, indicating they came from internal regions less exposed to galactic radiation. The scientists consider this finding crucial because it implies that the internal layers of the nucleus preserve more primitive characteristics that could reflect the conditions of the stellar system where it formed. That these particles emerged after perihelion suggests that the heat released from the interior continued to cause surface fractures, a process that allowed access to fresh material. The spectra related to complex organic compounds also showed important nuances at this stage. Although no highly complex molecules were detected that could lead to misinterpretations, patterns did appear that suggest the presence of partially formed organic chains. This does not imply biological activity or anything similar, but purely chemical processes that can occur in dust grains exposed to radiation for extremely long times. These processes are of enormous interest to astrochemistry because they allow comparison of how organic matter evolves in environments different from those controlled by a star. In this sense, each molecule detected in 3I Atlas represents a clue about interstellar medium chemistry and how materials aggregate in foreign protoplanetary disks. The scientists also used this stage to refine dynamic models about how interstellar objects move through the galaxy. The trajectory of 3I Atlas allowed evaluation of how small perturbations during its journey could have shaped its internal structure. It is likely that it experienced interactions with molecular clouds, intense radiation regions, or even gentle collisions with dense interstellar particles. These interactions, though subtle, can gradually modify its surface, compact the dust, and chemically transform the outer ices. The evidence observed in 3I Atlas, transformed ices, compacted dust, and activity dominated by carbon dioxide, fits with an object that not only traveled for millions of years but also passed through physically diverse environments before reaching our solar system. Moreover, the comparison with 2 revealed an intriguing contrast. While 2 showed a composition more similar to solar system comets, 3I Atlas appeared far more extreme and singular. This led some specialists to propose that objects like 3I Atlas could come from stellar systems with radically different compositions from that of the Sun. The carbon dioxide abundance could be related to carbon-rich young disks, perhaps formed in galactic regions with higher density of heavy elements or with colder conditions during the early formation stages. Another aspect that drew attention was the unusual shape of the coma. Some visual records showed asymmetries that did not match the typical behavior of a comet affected by solar wind pressure. Although no evident fragmentation was detected, the dust distribution suggested that the nucleus surface might be emitting material from specific zones rather than uniformly. This type of directional emission can occur when gas jets escape through internal cracks that channel the material outflow. In local comets, these jets usually align with regions where water ice or carbon monoxide ice is directly exposed. In 3I Atlas, however, the directions did not correspond to surface temperatures, suggesting that the jets originated from internal points activated late. Lastly, the scientists reflected on what all this might mean for understanding future interstellar objects. If 3I Atlas represents only one type within a broad diversity, then each object that arrives will offer new characteristics that will further expand the understanding of how solid materials form in different stellar systems. The idea that 3I Atlas is an extreme example does not diminish its value. On the contrary, it turns it into a key piece for mapping the complexity of the galaxy through the travelers that occasionally cross our path. As 3I Atlas continued slowly moving away from the region where solar radiation exerts its strongest influence, the analysis teams took advantage of this phase to compare all the data collected before, during, and after perihelion. This comparison revealed a set of patterns that, when placed side by side, showed surprising coherence in the object's behavior. What initially seemed a collection of isolated anomalies, the extreme abundance of carbon dioxide, the reddish dust coloration, the deep negative polarization, the delayed activity, and the persistence of organic emissions, began to reveal a clear narrative about the chemical and physical history of 3I Atlas. Each datum reinforced the idea that it is an object formed in an environment totally different from that of the solar system, an environment where the composition of the protoplanetary disk, the local radiation, and the freezing processes gave rise to an internal structure unlike that of any familiar comet. One of the elements that most caught attention at this stage was the way the thermal evolution models began to align with the actual observations. The scientists had been adjusting the simulations to try to reproduce the behavior of carbon dioxide at different depths, and the results suggested that the distribution of carbon dioxide within the nucleus could be the product of an extremely slow freezing process in a carbon-rich environment. This would imply that 3I Atlas formed in a region of the protoplanetary disk where the temperature was low enough to allow carbon dioxide to accumulate as a major component rather than being relegated to surface layers. In solar system comets, carbon dioxide is usually present but in much smaller proportions, because the initial temperatures do not allow it to become the dominant ice. The composition of 3I Atlas completely defies that pattern. Another crucial aspect was the evolution of the dust. As the object continued cooling, the observations showed that the dust emitted after perihelion had a slightly different reflectance from that observed during the approach phase. Although this change was subtle, it had profound implications. It meant that the particles emitted at different stages came from layers with differentiated compositions. During the approach phase, the dust was dominated by materials heavily processed by galactic radiation, while after perihelion particles began to appear with fresher optical signatures, less modified and closer to the original nucleus composition. This transition allowed the teams to directly compare the surface dust exposed for millions of years with the internal dust preserved from the interstellar environment. This opportunity is extremely rare because local comets lose their primitive layers after repeated solar visits, something that does not happen with an interstellar object like 3I Atlas, which is probably experiencing its first significant heating since formation. The gas dynamics also revealed something fascinating. Although the overall activity was declining, some late spectral lines showed punctual peaks that repeated irregularly. The researchers suspect these peaks could be related to the nucleus rotation that exposed different regions to variable temperatures even during the outbound phase. If certain internal cavities acted as reservoirs of trapped volatiles, their late release could produce intermittent emissions. This type of complex behavior fits the porous and heterogeneous internal structure that the simulations began to describe. Moreover, it reinforces the idea that the nucleus is far from a uniform solid block. Rather, it appears to be an assemblage of materials with distinct physical histories, assembled in a stellar environment that may have experienced variability events in its youth. The ion tail also continued to provide valuable data, although most comets present an ionic tail that fades quickly after perihelion. In 3I Atlas, this structure remained active longer than the models predicted. This suggests that the released compounds continued to be ionized by the solar wind due to their composition and the speed at which they dispersed in space. The fact that this tail remained for so long indicates that even in late phases, the comet continued to release volatiles that interacted with solar radiation at a distance where significant activity would normally no longer be observed. The scientists also placed special importance on the data related to simple organic molecules. Although their presence in comets is not a surprise, what drew attention was the persistence of these molecules in 3I Atlas even under lower temperature conditions. This could mean that the nucleus contains organic materials that have never been exposed to high heat levels and are sublimating for the first time. These compounds could have been synthesized in the protoplanetary disk where the object formed, or they could be the product of reactions induced by cosmic rays in the interstellar medium. In any case, their prolonged presence suggests that 3I Atlas preserves molecules that have survived intact for extremely long times, turning this object into an unprecedented chemical time capsule. Another key point was the analysis of how the activity of 3I Atlas compared with that of local objects after perihelion. The most notable difference is that while solar system comets show a clear pattern of declining activity, 3I Atlas maintained a sustained level of chemical and dust emission, albeit with fluctuations. This led the experts to conclude that the internal composition is highly stratified with materials that respond differently to thermal energy. This stratification implies that the comet may have experienced very different accumulation processes, possibly the product of a protoplanetary disk with more extreme temperature gradients or with chemical proportions different from those of the solar system. At this stage, the scientific consensus began to form around a clear idea. 3I Atlas is not only an interstellar comet different because of its composition, but it also represents a type of object whose structure and evolution are not described by the models developed for solar system bodies. This implies that the standard models are not sufficient to explain its behavior and that new approaches will be necessary that take into account the chemical and physical diversity of interstellar bodies. Finally, the scientists agreed that what was observed in this phase not only expands knowledge about 3I Atlas but also sets a precedent for the interpretation of future interstellar objects. As next-generation telescopes come into operation, more objects of this type are expected to be detected. When that happens, the data from 3I Atlas will serve as a fundamental reference for understanding how diverse the chemistry, structure, and activity of the travelers that cross our solar system from other corners of the galaxy can be. As 3I Atlas continued moving even farther from the Sun, the teams continued refining every available data set to understand how the internal structure of the nucleus influenced the late activity of the object. At this stage, the observations showed that the decrease in gas production did not follow the uniform pattern usually seen in local comets. In many cases, when a comet passes perihelion, its activity decays along a smooth curve that reflects the temporary depletion of the most superficial volatiles. However, 3I Atlas displayed an irregular decline with intervals of activity that seemed to ignite in a punctual way, as if the nucleus were releasing material trapped in internal chambers with significant delay. This behavior reinforced the idea that the comet possessed an extremely complex internal structure, possibly consolidated in an environment that never experienced repeated thermal cycles as solar system comets do. One of the hypotheses that gained strength was that 3I Atlas could contain layers of ice that have never been exposed to high temperatures since its formation. The reasoning behind this theory is straightforward. If this object was ejected from its stellar system early and traveled for millions or perhaps billions of years through interstellar space, then it is perfectly possible that most of its interior has remained frozen at extremely low temperatures since its origin. This preserved condition explains why the compounds released during the post-perihelion stage included relatively fragile molecules that in local comets degrade much earlier. The fact that these molecules appeared late in 3I Atlas indicates that the internal layers were only then experiencing significant heat for the first time in their history. The teams also noted something peculiar in the spectral analyses related to surface temperature distribution. Some sectors of the nucleus appeared to maintain higher temperatures than expected, even when the comet was already far enough from the Sun to have returned to a stable thermal regime. This phenomenon could be explained by the low thermal conductivity of the internal material. If the nucleus is extremely porous with cavities filled with volatiles, then heat can remain trapped in certain regions for long periods. This not only prolongs the sublimation of internal gases but also modifies internal pressure, which can lead to additional fractures that allow the escape of fresh material. The persistence of carbon dioxide continued to be one of the most striking aspects. At this point in a typical comet, carbon dioxide should have decreased considerably. However, 3I Atlas maintained detectable levels suggesting that its internal distribution of volatiles does not follow any known model for solar system comets. This difference was not interpreted as an anomaly, but as compelling evidence that chemistry in protoplanetary disks of other stellar systems can be radically different. In fact, the specialists began to speculate that 3I Atlas may have formed in an environment where the water-to-carbon dioxide ratio was much lower, allowing carbon dioxide to freeze in massive quantities and become deeply trapped in the nucleus structure. Dust dynamics studies also provided unique data. Some instruments detected that the particles emitted at great solar distance continued to show unusual optical characteristics. Unlike the typical dust of local comets, which tends to have porous structures and moderately reddish tones, the dust of 3I Atlas remained darker, more compact, and less reflective. This reinforces the idea that interstellar dust subjected to millions of years of cosmic radiation acquires physical properties not found in solar system materials. These compacted grains, possibly coated with dark organic layers, respond differently to sunlight, generating scattering and polarization patterns that continue to intrigue researchers. The ion tail, which should have dissipated gradually, displayed highly particular irregular behaviors. There were moments when the tail appeared to intensify briefly, something that does not fit conventional models. The researchers attributed this variation to the persistence of carbon dioxide and to the release of gases from deep nucleus cavities. When these gases are ionized by the solar wind, they generate prolonged structures that can appear even when the object is already moving away from the Sun. This observation is fundamental because it demonstrates that the activity of an interstellar object can last much longer than that of a local comet, depending on its internal composition and prior thermal history. The analysis of simple organic molecules also continued to yield interesting results. Although no complex molecules were detected, the sustained presence of radicals such as cyanide and signals associated with short organic chains suggest that the comet contains a chemical inventory rich in organic precursors. This does not imply anything related to life, but to the chemistry typical of dense, cold environments where materials aggregate under conditions not replicated in the current solar system. The persistence of these molecules indicates that they are being released from layers that were protected from degradation for extremely long times. Comparisons with local comets continue to be a key point at this stage. For example, in solar system comets a clear pattern is observed in the relationship between dust and gas production, especially regarding water sublimation. In 3I Atlas this relationship was not fulfilled. There were moments when the amount of emitted dust did not correspond to the amount of detected gas, suggesting that the processes governing the comet's activity are different from those of objects that have orbited the Sun since their formation. This discrepancy led the specialists to propose alternative models in which the internal structure of the nucleus plays a more determining role than solar radiation in the overall dynamics of the object. Another point that reinforced this conclusion was the detection of slight variations in the comet's thermal spectrum as it continued cooling. Some instruments detected that certain regions of the nucleus did not lose heat at the expected rate. This thermal retention is consistent with the presence of internal cavities filled with volatiles, implying that the nucleus could be formed by a network of ice mixed with low thermal conductivity dust. This type of structure could have arisen in an environment where material consolidation processes were slow and where perpetually low temperatures prevented the ices from redistributing or compacting in the standard way. At this stage of the study, the general consensus among the scientists was that 3I Atlas not only provides new data but is also establishing a reference point for how to interpret the late activity of an interstellar object. Each detection of residual gases, each variation in the ion tail, and each change in dust reflectance represented an essential piece for understanding how an object formed outside the solar system responds to stellar radiation for the first time. As 3I Atlas advanced through a region where the sun's influence began to lose strength, the researchers took advantage of this period to analyze in greater depth the final variations in its activity. Although the object had already passed perihelion some time ago, the instruments continued to record chemical signals intense enough to allow precise comparisons between the pre- and post-approach phases. This stage is especially valuable for scientists because it reveals how an interstellar object responds not only to the sudden heating it suffers when approaching the sun, but also to the gradual cooling process that occurs when it returns to the darkness of deep space. With solar system comets, the loss of activity usually follows well-studied patterns, but 3I Atlas, as it has demonstrated in every phase of its trajectory, again behaved in a way that does not entirely match those models. One of the first elements that drew attention during this stage was that the carbon dioxide emission persisted longer than expected. Despite the natural decrease in incident solar energy, some activity peaks continued to appear intermittently. This reinforced the idea that the internal structure of the nucleus contained deep deposits of carbon dioxide trapped in isolated cavities that were only then experiencing changes due to the heat absorbed during perihelion. The thermal simulations adjusted with the new data suggested that heat propagation inside the nucleus occurred very slowly, possibly due to a combination of highly porous material and internally compacted regions that acted as thermal barriers. This type of internal structure allows deep layers to take weeks or even months to release their content, which is reflected in the prolongation of the activity detected at considerable solar distance. The dust also continued to provide relevant information. The reflectance of the emitted particles showed variations indicating that both surface and internal material were leaving the nucleus during this late phase. The more internal particles, released slowly due to delayed heating, displayed slightly less reddish colors than the highly irradiated particles observed in earlier stages. This was interpreted as a clear sign that the object had begun to reveal its more primitive composition. In any solar system comet, this type of analysis is extremely difficult because the multiple solar passages degrade and process the surface layers of the nucleus, erasing traces of its original composition. With 3I Atlas, however, the absence of prior thermal cycles allowed access to much more representative material of its origin. During this period, important data were also recorded regarding the density and velocity of the expelled gas. Although overall production was declining, some episodes displayed abrupt variations that seemed to coincide with possible internal fractures. When a nucleus experiences uneven stresses due to heating, it is common for certain zones to collapse or fracture, releasing trapped gas. In the case of 3I Atlas, these fractures appear to occur less predictably than in local comets. The researchers believe this could be due to the heterogeneous distribution of volatiles and to the highly differentiated composition of the internal layers. Moreover, the localized carbon dioxide activity in specific zones suggests that the nucleus structure does not follow the typical patterns of vertical stratification, but could be a complex mixture of ices and dust assembled under very different conditions from those of the solar system. The simple organic radicals also displayed particular behaviors. Although their signals were generally decreasing, some compounds continued to appear during short intervals. This could be related to the release of partially processed organic chains trapped in deep ice. This finding has important implications for astrochemistry, as it suggests that certain compounds can survive long periods in interstellar space without complete degradation, even when exposed to cosmic radiation for millions of years. The scientists emphasize that although the presence of these molecules has no relation to biological processes, it does represent a unique opportunity to study how organic precursors behave in cold, dark environments far from active stars. The dust dynamics in the tail also presented interesting changes. As the comet moved away, solar wind pressure decreased, but some dust streams appeared to remain more defined than usual. This suggests that the emitted particles had electrical or physical properties that allowed them to interact with the solar wind in a prolonged manner. It was also observed that dust distribution in the tail did not disperse as rapidly as in local comets, reinforcing the idea that the particles of 3I Atlas are denser, more compact, and possibly coated with resistant organic materials that alter their response to radiation. Another important point was the estimation of mass loss. Although the figures are still being refined, preliminary data indicated that the amount of material expelled by 3I Atlas was less than expected given the unusual carbon dioxide activity. This implies that despite its prolonged activity, the nucleus may have conserved more mass than anticipated. If this datum is confirmed, it will be crucial for determining whether the nucleus structure is composed of materials with greater internal cohesion or whether the most active volatiles are concentrated in deep deposits rather than on the surface. The interpretation of all this led the scientists to an important conclusion. The late evolution of 3I Atlas cannot be described with standard cometary behavior models. This not only highlights its interstellar origin but also raises fundamental questions about how protoplanetary disks and other stellar systems produce solid bodies with properties so distinct from those of solar comets. The extreme carbon dioxide abundance, the persistence of simple organic compounds, the thermal heterogeneity, and the diversity in the dust cannot be explained if an internal structure similar to that of solar system comets is assumed. Finally, this late phase revealed something crucial. 3I Atlas not only provides information about its internal composition but also about the physical history of the interstellar medium through which it traveled. Each molecule released at this stage represents an opportunity to learn how chemical and thermal processes work in regions where direct observation has never been possible, and as the object continues moving away it continues to act as a living archive of an environment completely alien to ours. As 3I Atlas continued its advance toward ever colder and darker regions of the outer solar system, the researchers took advantage of this crucial phase to integrate all the data gathered during months of continuous observation. At this stage, the object was already far enough from the Sun for most surface activity to diminish, yet still close enough for instruments to capture weak but valuable signals of its composition and behavior. This transition between an active comet and a body in thermal rest state became especially interesting because it allowed analysis of how an interstellar object stabilizes after being exposed, perhaps for the first time in millions of years, to the intense heat of a star. One of the most studied areas during this phase was the evolution of the remaining dust in the coma. Although dust density decreased as activity decayed, the optical properties of the particles continued to reveal patterns about the internal structure of the nucleus. Some particles displayed less reddish tones than in previous stages, suggesting they came from deep layers not exposed to the interstellar environment for long periods. In contrast, other particles maintained the intense coloration characteristic of material processed by galactic radiation. This simultaneous mixture of surface and internal particles allowed a more detailed X-ray view of the comet, revealing an internal structure composed of multiple chemical and physical levels that evolved at different moments in its history. Comparative models with solar system comets indicated that this duality in the dust is extremely rare. In local comets, surface dust is dominated by materials that have already undergone multiple thermal cycles. In each solar approach the outer layers sublimate and expose new ones that are then also processed. In 3I Atlas there is no such cycle history, so the material exposed after perihelion represents two different moments in its history. The surface shows millions of years of interstellar exposure, while the interior preserves an almost intact record of its formation. This contrast turns the object into a unique opportunity to study how galactic radiation modifies solid material and how the interior of an interstellar body remains unaltered since its origin. Another aspect that captured the scientists' attention during this phase was the persistence of weak emissions of certain simple organic compounds. Although most of these signals were declining, some continued to appear in irregular patterns. This behavior suggests that the heat absorbed during perihelion continued to propagate slowly through the nucleus, activating small pockets of organic material trapped in internal cavities. These deep regions, which had never been heated before, began to release organic compounds in very small but detectable quantities. The late release of these compounds is particularly important for astrochemistry, as it indicates that the deep ice of an interstellar object can preserve molecules for time so long that they challenge models of chemical stability in cold regions of space. The researchers also used this phase to analyze how the carbon dioxide activity finally began to stabilize. Although this compound dominated the comet's emissions throughout its approach and part of its departure, the levels began to adjust to what was expected at greater distances. This late though delayed decrease helped calibrate models that describe how carbon dioxide trapped in extremely porous nuclei behaves. However, despite the decrease, Its presence for so long made clear that the carbon dioxide distribution in 3I Atlas does not follow the simple layered structure observed in local comets. Everything points to this object having a deeply integrated mixture of carbon dioxide ice within the nucleus matrix, a characteristic that can only be explained if the object formed in an environment with extreme carbon abundance under extremely cold conditions. At this stage, variations in the comet's residual tail were also studied. Although much of the ionic tail had dissipated, some weak traces continued to appear at certain wavelengths. This indicates that residual volatiles still interacted with the solar wind. The persistence of this interaction reinforces the view that the object is not only rich in carbon dioxide but also contains other compounds with very low sublimation rates capable of remaining active even under low radiation conditions. This type of behavior is not typical in solar system comets, whose main volatiles are depleted more quickly when moving away from the Sun. Another crucial point at this stage was the detailed analysis of the nucleus surface brightness. Although the resolution does not allow direct observation of the comet's surface, the changes in overall brightness offer clues about possible material redistribution after the intense activity. The models suggest that some of the expelled material may have redeposited on the surface, generating a return layer composed of freshly exposed internal dust. This phenomenon, though it also occurs in solar comets, acquires special meaning in interstellar objects because that internal material more directly reflects the conditions of the environment where the object formed. During this phase, the scientists also took the opportunity to study how the internal structure may have been modified during its passage through the solar system. Although no signs of fragmentation were detected, the prolonged activity and the moderate though present mass loss probably altered some internal cavities. Although these modifications do not change the overall structure of the object, they probably generated new internal pathways for residual volatiles, explaining part of the late activity observed. These internal changes could serve as a reference for studying how interstellar objects lose mass or evolve structurally when passing through a stellar system. In summary, the distant phase of the journey of 3I Atlas allowed some unknowns to be resolved but also opened new questions about the diversity of interstellar objects. The persistence of carbon dioxide, the late release of organic compounds, the mixture of surface and internal dust, and the variations in gaseous activity indicate that the internal structure of the object is far more complex than thought. This stage demonstrated that even when activity decreases, an interstellar object continues to be a continuous source of valuable information about its origin and its history. When 3I Atlas reached the distance where it practically ceased to show detectable activity, the scientists found themselves with an exceptional opportunity to analyze an interstellar object almost in a state of rest after having experienced its first significant approach to a star in millions of years. This final stage of the study not only allowed observation of how the comet stabilized after solar heating, but also to infer how it might behave in the future as it slowly leaves the region dominated by the Sun's gravity. Unlike solar system comets that return again and again, 3I Atlas will not return. This means that everything learned during this unique transit represents the only available window to study its behavior in all possible phases. One of the first aspects the researchers examined during this stage was the total dissipation of the coma. At first, even at great distances, weak traces of dust and gas were detected, but over time the emission fell below observable thresholds. This complete disappearance of activity provided a reference for adjusting models about the thermal conductivity of the nucleus. The simulations compared the time elapsed since perihelion with the exact moment when detectable activity ceased. The results suggest that the comet's internal structure retained heat for a longer period than expected, a property directly associated with its extreme porosity and with cavities filled with volatiles that took weeks to stabilize. Once the activity finally dissipated, it became clear that the nucleus possesses low thermal conductivity, something consistent with an object that spent its existence in a cold and relatively isolated environment. Another key point in this final stage was the analysis of the nucleus residual brightness. Although the coma was no longer present, the nucleus continued to reflect sunlight, and that reflectance allowed estimation of some surface properties that had not been possible to calculate while the coma was active. The models indicated that the object's albedo was extremely low, which matches the hypothesis that its surface is coated with a mixture of complex organic materials and dark dust darkened during long periods by galactic radiation. This type of coating, also observed in some trans-Neptunian objects, becomes even darker in interstellar bodies because their surface has never been renewed by cyclic activity as occurs in solar system comets. This confirms that the surface of 3I Atlas is one of the oldest and most chemically modified surfaces ever studied from Earth. Meanwhile, the final chemical analyses took advantage of every residual spectral trace to identify possible molecules of extremely slow sublimation. Although gaseous activity was almost imperceptible, the most sensitive instruments managed to identify marginal signals associated with highly volatile compounds, possibly remnants of molecules trapped in internal layers that were released at minuscule rates. These detections at the very limit represent enormous scientific value because they indicate that even under low radiation conditions, some compounds can continue migrating slowly toward the surface. This type of behavior has been observed in some ice-rich asteroids of the outer solar system, but it had never been documented so clearly in an interstellar object. The detection suggests that the internal structure of 3I Atlas can be so cold and inert that it allows the preservation of volatiles over time scales that exceed any known thermal cycle in local bodies. The scientists also began to project models about the object's future trajectory, although they already knew it would never return to the solar system. It was important to calculate how its slight mass loss could marginally alter its hyperbolic path. These adjustments, though subtle, help understand how interstellar objects can change course after brief interactions with stars or high-radiation regions. In the case of 3I Atlas, the calculations indicate that its internal structure was not sufficiently disturbed to significantly modify its path. This implies that the passage through our solar system was gentle enough not to cause fragmentation or massive mass losses, which also confirms the overall cohesion of the nucleus. At this stage, much was discussed about the scientific relevance of the object. Beyond the exotic composition and unusual activity, 3I Atlas represents an unprecedented opportunity to study how solid bodies form and evolve in stellar systems completely alien to ours. Its carbon dioxide richness, its highly processed dust, its combination of fresh internal and aged external materials, and its prolonged activity form a coherent set of properties that expand the very definition of what an interstellar comet can be. Researchers from multiple institutions agree that this object could become a mandatory reference for all interstellar bodies detected in the future, not only for what it revealed but for what it forces us to reinterpret about our understanding of the galactic medium. Moreover, the object has demonstrated that the models used to understand solar system comets must be adjusted when dealing with interstellar visitors. The behavior of carbon dioxide, the persistence of simple organic compounds, and the dust dynamics indicate that the chemistry and physics of these objects cannot be explained with the same theoretical frameworks. This realization marks the beginning of a new era in modern astronomy, where each interstellar visitor is expected to contribute additional pieces to a puzzle we are only just beginning to assemble. Finally, this last phase of the study left a clear message among the scientists. 3I Atlas is not only a physical archive of another stellar system, but also direct evidence of the extreme diversity that exists in the formation of solid bodies in the galaxy. Each released molecule, each ejected dust grain, and each detected thermal signal represents an ancient fragment of a place we can never observe directly. Its passage through the solar system was brief, but sufficient to transform our understanding of interstellar travelers and of the physical and chemical conditions that shape matter beyond our cosmic neighborhood.